This video will go over exactly what you need to know for mirrors and lenses on the MCAT. We're going to start off by talking about mirrors and parallel light rays. A lot of MCAT questions talk about light rays coming from an object, and they will enter at an angle whenever they hit the mirror or the lens. What parallel light rays are light rays that come in parallel to each other. And this happens anytime that the light source is very far away from the lens or the mirror. Or it could happen if the light source is something like a laser, because lasers are specifically designed to emit parallel light rays. Let's look at what happens to these when they hit a mirror or a lens. For converging or concave mirrors, the light rays hit the mirror and are reflected back, and they're all going to converge onto the same point. That point is called the focal point. For a diverging mirror, those parallel rays come in, and this time they get reflected away from each other. What you have to do for convex mirrors is draw a dotted line in the opposite direction of the reflected light. And if you do that for each ray, then you'll find that the dotted lines converge behind the mirror. And where those dotted lines converge is the focal point for a convex mirror. One important point about the focal length for mirrors is that it's equal to half of the radius of curvature. If you imagine your mirrors as part of a circle and then draw out the rest of that circle, the radius of that circle would be from the center to the mirror. The focal point will be exactly halfway between the center of that circle and the mirror. The pictures are not drawn perfectly, but where those light rays converge should be right between them. The same thing goes for the convex mirror. If we were to draw a complete circle, the focal point should be halfway between the center of that circle and the mirror. So if it was drawn correctly, those dotted lines would converge more like right here. Now let's look at what happens to those parallel light rays when they go through a lens. For a converging lens, the parallel light rays hit, and then while the light is in the lens, it's refracted, so it's bent and it exits the lens at a different angle. For converging lenses, those light rays will converge, and the point at which they converge is the focal length for that lens. For a diverging lens, the parallel light rays hit the lens, and as they travel through the lens, they're bent at an angle away from each other. Like what we did with the diverging mirror, we draw a dotted line back from those refracted rays, and the point at which all those dotted lines converge is the focal length for the diverging mirror. There is no focal point is equal to the radius of curvature divided by 2 for lenses, because the amount that the light is refracted is dependent on the material of the lens, not just on the curvature of the lens. For lenses, we can measure the strength of the lens based on the distance that the focal point is from the lens. The strength is equal to 1 divided by the focal length. So the closer that focal point is to the lens, the stronger the lens is, because it causes the light to be refracted more. Now we'll look at what should you do when the light rays are coming from an object that's not super far away. The light rays that come from that object are not parallel. And since it's not parallel rays, the light rays that are reflected are not going to converge at the focal point. There are things called ray diagrams, which are used to figure out where those light rays converge, or you can use the thin lens equation. The thin lens equation combines the focal length, the distance that the object is from the mirror, and the distance that the image is from the mirror. You use this equation and plug in whichever values are given to find whichever value is missing. And frequently what you're trying to find is the image distance. One of the most important things about using this equation is understanding what the sign conventions mean and how those affect where the focal point, the object, or the image are relative to the mirror. So let's walk through that for mirrors and lenses. The object is always in front of the mirror. The focal point for a concave mirror is in front of it, and the focal point for a convex mirror is behind it. Concave mirrors can produce images that are either in front or behind the mirror, but diverging mirrors can only create images that are behind the mirror. For mirrors, everything that's in front of the mirror has a positive distance, and everything that's behind the mirror has a negative distance, and that's for diverging and converging mirrors. Use your understanding of sign conventions and the distances of these things from the mirror to plug them into the thin lens equation and find your missing value. For example, if you're told that you have a diverging mirror with a focal length of 3, you would set this up by starting with 1 over negative 3. And then if you're told that your object distance is 2, you would do 1 over positive 2 plus 1 over I, and you can now solve for I to find the distance of the image from the mirror. If the number that you get for I is positive, then you know that it's in front of the mirror. If it's negative, then you know that it's behind the mirror. For a diverging mirror, since the focal point is always negative and the object distance is always positive, you will end up with a negative I every time because you'll be subtracting a positive value from a negative value, which always gives you another negative value. Once you have your image distance and your object distance, you can plug those values into the magnification equation. The magnification equation tells us what's the ratio of our image height to the object height. And if it's a positive sign, your image is upright. And if it's a negative sign, your image is inverted. So something like -2 tells us that our image is twice as big as the object and it's inverted. And lastly, anytime that you have a positive image, that is called a real image, and any negative image distance is a virtual image. And that is for all mirrors and lenses. Now we want to look at how all of this is applied to lenses. Most of it stays the same, but we have a couple sign convention changes. The object is always in front of the lens, just like with mirrors. The focal point for converging lenses is behind it, and the focal point for diverging lenses is in front of it. Converging lenses can create images that are in front or behind, but diverging lenses can only create images that are in front. The object distance, just like mirrors, is always positive, and here is where we see something different compared to mirrors. For the image distance and focal length, when it's in front of the lens, you get a negative sign, and when it's behind the lens, you get a positive sign. If you memorize those sign conventions, we apply the equations in the exact same way that we did for mirrors. Finally, let's work through an example to see how to apply this. And you can even use this approach to questions that don't give you actual values, and we'll see that with this one. A student places an object in front of a convex lens at a distance less than its focal point. Which of the following best describes the resulting image? If we sketch this out, we say the focal point is roughly right there, and we know that the object will be at a distance that's less than the focal point, but it has to be on the opposite side of the lens. Rather than trying to draw out the ray diagram for this, we can just make up some values that fit the situation described and plug them into the thin lens equation. You can make up any values you want as long as they fit the situation described. So let's just say that our focal point is a distance of 4 away from the lens. Then for the object distance, we just have to choose anything that's less than 4. So I'm going to choose 2. Then do plus 1 over I, and now we can solve for I. 1/4 minus 1/2 is equal to -1/4. So we have -1/4 equals 1 over I. Then we take the reciprocal to find I, so I is equal to -4. Since I is a negative value, we know that this is a virtual image, so we're between B and D. To figure out whether it's upright or inverted, we plug that in to the magnification equation, which gives us M is equal to -4 over 2. That's equal to 4 over 2, which is equal to 2. A positive magnification value tells us that the image is upright, and a value of 2 tells us that it's twice as big as the object. So our answer is virtual, upright, and enlarged.